Welcome back, everyone. Next, we have ASP Isotopes Inc. It trades on the NASDAQ under the symbol ASPI and is a pre-commercial stage advanced materials company dedicated to the development of technology and processes to produce isotopes for use in multiple industries. Happy to welcome back the CEO, Paul Mann. Nice to see you, Paul.
Nice to see you again. Thanks for having me back. And thank you to the audience for their interest in our company. So I will give the usual kind of 20-minute presentation. Then we have 10 minutes afterwards for Q&A. So we're a NASDAQ company, so just review these forward-looking statements. That'd be great. Our safe harbor disclosure on there. And so, what is ASP Isotopes? We're a company that makes very special chemicals. And, we've developed this technology over about 20 years or so. It comes from South Africa, where it's got a long history in nuclear engineering, a long history in chemical engineering. And isotopes are a particular chemical with a very challenging supply-demand balance and a very challenging supply backdrop, given most of them produced by Russia. And here on the right, you'll see some of our characteristics for the stock. So what is ASP Isotopes? Well, we now have 3 verticals. We set this company up 2.5 years ago, and we built this company over the last 2.5 years to have these 3 vertical kind of divisions. In the middle, you'll see ASP Isotopes, which focuses on producing stable isotopes for use in healthcare, technology, and other applications. And in there, we have 2 plants in South Africa, which will both become commercial and profitable during the middle of this year. We just started building our 3rd plant in South Africa as well. And our plan is to grow that business into Iceland in the next couple of years. On the left, you'll see PET Labs, which is a radioisotope company. It produces isotopes with maybe only sort of a 1 or 2 hour half-life. And so you have to produce those close to where they're being used. And PET Labs is South Africa's leading supplier of radioisotopes. And, our plan is to grow that business around the world in other jurisdictions over the next several years. And our view is if you can make a 70% gross margin in South Africa, a country with $6,000 per capita GDP, then that should allow us to make very good money in many other jurisdictions around the world. And on the right-hand side, you'll see Quantum Leap Energy, which is our business that's going to develop nuclear fuels for the future, specifically HALEU and lithium-6. And it's a desperate need for new sources of nuclear fuels. And we actually just raised some money into Quantum Leap last week, $20 million. And our plan is to spin that company out later on this year, and maybe IPO it and separate that business into a separate business with a different management team and different board directors. And we've always had the view that nuclear fuels and nuclear medicine are 2 very different businesses, and that's really the purpose for splitting that business out. In terms of our milestones for the next sort of year or so, our goal is to sign a few more supply agreements and to really become cash generating in that middle business, ASP Isotopes. Also, our plan is to start building enrichment facilities outside of South Africa, countries that benefit from cheap geothermal energy, places like Iceland. So what are isotopes and how do we make money from them? So isotopes, you touch them every day. You probably don't know it, but you do. They're in things such as computers and medicine and energy. And 85% of stable isotopes for healthcare come from Russia. That's led to a lot of challenges in the supply chain, both for the last 20 years or so, but specifically in the last 2 years. And what exactly are isotopes? Well, let's take silicon as an example. Silicon-28. So when you think about sand on a beach, sand is basically a form of silicon, and there are 3 versions of silicon: silicon-28, 29, and 30. And they're all silicon. They all have the same number of protons in the nucleus and the same number of electrons orbiting around the nucleus, but they've got different numbers of neutrons inside the nucleus. And that gives these isotopes different physical properties. They've got pretty much identical chemical properties, but different physical properties. And so, for example, silicon-28 is a very, very highly conductive. Silicon is used in semiconductors, but silicon-29 actually degrades from the conductivity. It hurts the conductivity. So if we can remove the 29 isotope and just have pure 28, the conductivity of that silicon, that semiconductor, goes up thousands of fold. And we're talking to a number of semiconductor companies who have need for silicon-28 in years to come, and actually right now as well. And we're likely going to sign some supply agreements with them fairly soon to commercialize that product. And when you think about how we price these products and how we make money out of them, silicon, if you had a bag of sand a kilo of sand, that's probably maybe $1 a kilo. But when we enrich it in the silicon-28 isotope, about $600,000 a kilo. For carbon, you take a bag of charcoal, a bag of carbon, that's maybe $1 a kilo as well. When we enrich it into carbon-14, it's about $24 million a kilo. So we take very basic, very normal elements, and we convert them into very specialized elements and have niche applications in specific industries and enable industries to do specific things that they need to. So how do we do this? Well, we have two technologies, both developed over the last 20 years in South Africa by our scientists. The first is the ASP process, or aerodynamic separation process, and the second is quantum enrichment. So the ASP process is basically a stationary wall centrifuge. We spin the gas very quickly inside the tube. It's approaching the speed of sound. And the heavier masses go to the outside of the tube, the lighter ones go to the inside. And then we use certain specially designed flow directors and flow valves to direct the heavier isotopes into one stream and lighter isotopes into another, and allows us to separate them out. The advantage of this technology is there's no moving parts other than the compressor. These parts are small, modular, they're scalable, they're very, very effective at producing small quantities of very valuable products. Quantum enrichment uses a laser, and so we basically it's very useful in enriching isotopes that can't be turned into a gas. So we can heat a metal up into a vapor. We pass that vapor through a laser, and that laser ionizes or charges one of the isotopes, and then we're able to extract that isotope using a charged plate. And we'll talk more about where we're going to use that later on in this presentation. So as I said earlier, our processes are cost-effective, they're modular, they're scalable, and very environmentally friendly. We don't have any nuclear or chemical waste from our plants. So here's a map of isotopes we expect to enrich over the next several years. And you'll see some of them are starting up this year, and others next year, and others in year to come. But a lot of these are focusing on nuclear medicine or pharma and agrochemicals, and others on nuclear energy. So this slide, which is a bit distorted here, shows how radiomedicine has changed over the last several years. And you'll see, we've really evolved a lot from very basic forms of radiation, 20, 30 years ago, to where we're now getting highly specialized diagnostics and therapeutics to treat very specific diseases using alpha therapeutics and beta therapeutics, radioactive particles that can destroy tumors very accurately if they're deployed correctly. So this slide just shows our iron markers. Again, it looks like it's been damaged a little bit while sending it across to emergent growth this afternoon. But these show the isotopes that are of interest. At the top here, you'll see the stable isotopes, ASP isotopes will produce. At the bottom here, you'll see radioisotopes that PET labs will produce using a stable isotope. So you take a stable isotope and you convert it into a radioisotope at the point of care or close to the point of care. So, for example, molybdenum-100 is a stable isotope. You can ship it in a FedEx package or any other postal means you want to. And then you can convert it to technetium-99 at the point of care. It has a six-hour half-life. And so you can't really ship technetium-99 much more than sort of, maybe 9 hours maximum. And so you see there's a great symbiotic relationship between ASP isotopes and PET labs. So this is a picture of our first plant in South Africa. This produces carbon-14. And you'll see these 5 kind of cases here. Each of those cases or metal boxes is about 2.2 meters high by 2 meters long by 1 meter wide. And this plant here should be able to produce the entire world's demand of carbon-14. We've signed a contract with a Canadian customer, and they will supply the feedstock. We will enrich the feedstock. They'll supply 0.5%. We'll enrich it up to 85%. And then we'll charge a fee for that. And Our minimum expected revenue from that is $2.5 million a year. This plant could provide a lot more than that, and there's been real pent up demand for this product, we feel right now. So maybe we'll do more than the 2.5 minimum that we're kind of expecting. So molybdenum 100. Again, I apologise. These slides appear to have been scrambled a bit in the email for myself here in London to emerging markets, but emerging growth. But this chart here just shows exactly how molybdenum can be used to potentially produce technetium-99, which really is the workhorse of nuclear medicine. And today, technetium-99 is produced from molybdenum-99. And molybdenum-99 has a 66-hour half-life, so every 2.5 days, your product loses half its value. Molybdenum you can ship very easily and convert it at the point of care. This slide's really been scrambled, but this is for zinc. And so zinc is an emerging diagnostic. So with zinc, you can produce gallium-68, and gallium-68 is really required to diagnose tumors that can be treated with lutetium and actinium-based drugs that are in development. And we expect to start producing zinc-68 in about the middle of next year. And as I say, there's a huge growing demand for it because of these new drugs that are coming to market. So this is ytterbium-176, and we started building our first ytterbium-176 plant about in November, December last year. And there's a huge growing need for ytterbium-176. Novartis's new oncology drug called Pluvicto requires lutetium-177. It's a very hard radioisotope to produce. And so we expect to be able to produce this middle of next year as well. And we have a lot of demand for this isotope, This next slide just talks about quantum computing. I've already kind of explained it, but we'd expect to start supplying silicon-28 in the next 12 months or so. We have a lot of interest from semiconductor companies that need large quantities of silicon-28 in the years to come. Anna, can I ask you, can you hear me okay?
Yes, we can hear you perfectly.
Fantastic. I'm just checking because my screen has paused, and I'm operating remotely today in London, so I just wanted to check. Thank you. And so moving forwards to our future plans to scale the ASP Isotopes business, our plan is to grow into Iceland. We use a lot of energy in ASP processing. We spin a gas inside a tube. We have to compress it, and so South Africa is known for its poor energy supply. We have 1.5 megawatts of diesel generation outside one of our plants for during times of load shedding when the electricity gets shut off. So we've signed kind of an LOI with an energy company in Iceland to have a large amount of energy at less than 5 cents per kilowatt hour. We've also found some real estate. We'd expect to start signing contracts for build plants in Iceland in the next sort of 6 months or so. And our expectation is the customer is going to supply a lot of the capital to build these plants. So we're using someone else's balance sheet to kind of grow our business. We'll move now on to Quantum Leap Energy. And this is a part of the business where I get most questions and a lot of interest right now. So, listen, the problem the world is facing is fairly well known. As during the next 25 years, we have to double the amount of electricity production. And at the same time, we have to achieve carbon neutrality. In our view, protesting is not going to solve this problem. We'd like to be part of the solution. That's going to require innovation and investment. Now, I shouldn't have to explain why we need more green nuclear energy. Solar and wind are fantastic, but when there is no sun and is no wind, it's kind of a problem. And these two slides here just really talk about the reasons why solar is so efficient, and nuclear is so efficient and so controllable and so inexpensive and very environmentally friendly. So, the future of nuclear power in our view is the SMR, the small modular reactor. So when you think about motor cars and the production of motor cars, what drove the cost of a motor car down was the Ford Model T, taking a car onto a production line. And this is doing the same thing with nuclear power. If you can put a nuclear power station, the production of it or the engineering of it onto a production line, producing lots of the same type over and over, you can really bring the cost of construction down dramatically. So these plants are going to be much smaller in size versus the nuclear reactors of yesteryear. I think that the future of 2 gigawatt reactors, where it takes 10 years to build and $10 billion, and you typically find it takes 20 years and costs $20 billion. They're not going to happen in the future, I guess. They need huge amounts of transmission lines to get that energy away from where it's being produced to a location where people can use it. So some of the companies involved in these small modular reactors, Terra Power, that's Bill Gates' company, X Energy, that's Cam Garfassian's company, Rolls-Royce, Oklo's missing from this chart, that's Sam Altman's company. And these companies in DOE have invested billions of dollars to try and get these new forms of nuclear reactor to the market. The problem for these reactors is they all require a new form of nuclear fuel called HALEU, high-assay, low-enriched uranium. And there is no Western producer of that fuel right now. The hope was that Russia would supply it. That's no longer an option. And so most of these nuclear reactors have been delayed by at least 2 years or more. And the chart here to the right shows what the Nuclear Energy Institute believes the growing demand for HALEU looks like just in the US. But based on our discussions with potential customers, we think there's a lot more than what this chart here shows. So this slide really has gone wrong during transmission from myself to you guys. But the important line on this chart here is the selectivity line, the alpha. And you'll see, for centrifuge, which is how one typically enriches uranium today, the alpha, or the selectivity, the enrichment factor, it's about 1.15. We've developed a process called quantum enrichment where the selectivity is much greater. It's greater than 50. And so this allows us to do a lot more enrichment per stage of enrichment. You've kind of seen this slide earlier. This is kind of how we do it. And so let's just talk about the nuclear fuel supply chain quickly now. Again, this slide seems to have been garbled a bit too. But when you process uranium into low-enriched uranium, there's a mining and milling component of it, the conversion, and then the enrichment. And the enrichment is the part that we are interested in. And if you look at this chart here, you'll see that all components of the nuclear fuel supply chain are trading at 10, 20-year highs. There's a huge shortage of nuclear fuel right now, and it's not clear how a lot of reactors are going to get the fuel they need to operate. So what does this mean for HALEU prices? Well, you'll see this chart on the left here. Most of these reactors were being designed when HALEU prices were $5,000 to $10,000 a kilo. Right now, you're talking at more than $20,000 a kilo. And on the right, you'll see that the ore, the part you dig out of the ground, is about $11,000. The enrichment component's about sort of $6,500, and conversion is about $6,000 for $2,500. And so what you'll find is a lot of the math behind SMR is struggling right now, given the extremely high cost of fuel. And it's not clear how one can solve this problem, given how long it takes to increase supply chains, increase supply. When you think about it, going back to this previous slide here, the uranium price has gone up almost fivefold over the last couple of years, and we have not even seen a supply response to it yet. It's unusual to see a commodity go up fivefold in price and not see a supply side response. When you look at the enrichment part on the right here, that's gone up threefold over the last sort of 3 years or so. And again, there's been zero supply side response to this, really. And again, the conversion part up threefold, and again, not much of a supply side response. So, there's a real problem looming in the nuclear fuel market. And we're going to be able to solve that problem. So we've signed 2 MOUs with large US-based SMR companies who collectively require over $30 billion of HALEU. And our goal is to build a plant using quantum enrichment to provide that fuel for them. One of the reasons why I think people are excited about our technology is that because our enrichment factor is so high, it allows us to take other people's nuclear waste, these depleted tails, and convert it into HALEU. So this picture on the left here shows a nuclear site in Ohio, and each of these little canisters contains 20 metric tons of depleted uranium hexafluoride, and it's sitting there just growing by 30,000 metric tons per year. and no one knows really what to do with it. And our goal is to be able to take this waste and convert it into really efficacious fuel the world can use in the future. And that'll both really bring down the cost of HALEU as well as clear up an environmental problem. And I think finding a solution to cheap HALEU is really what's going to solve the energy crisis looming over the next 25 years. Unless you can price nuclear fuel at a discount to hydrocarbon-based fuel, emerging markets are not going to use it. And so it's really important we find a cheap source of nuclear fuel. We believe this could be the future there. So just to summarize, we have two proven and proprietary technologies developed over the last 20 years. There's multiple geopolitical tailwinds that are helping our industry right now. And, our goal is to, we've only started this company up 2.5 years ago. Our goal is to be cash flow positive, by the middle of this year, around the middle of this year, and then start to grow and build from there. So Anna, I'll stop there and I'll take any questions.
Great job. Okay, let's jump into some of these questions for you, Paul. First of all, is PET Labs currently producing revenue or not yet?
Yeah, thanks. So PET Labs is currently producing revenue, and our goal is to triple the size of that business over the next couple of years. We made an announcement in November that we're going to add 2 more cyclotrons into South Africa. This will bring a lot of healthcare benefits to the people of South Africa. And, it's really doing a lot to improve our relationship with the South African regulators and government bodies and what have you. And PET Labs is a great business. I mean, it's a leading supplier of radioisotopes in Africa. And we actually give away all of our drugs to children under the 18 free of charge. We don't think it's appropriate for children who are suffering from cancer for their families to have to try and find the financial resources to treat them. So we do a lot of goodwill to society as well, and it generates very, very good, consistent profitability.
Good to hear that. Larry Reed asks, with your process, is there any risk of enhancing the isotopes to the point of the atom decay?
Yeah, I'm not quite sure what one means by atom decay, but in our process, in terms of SMR and quantum enrichment, no, that's not possible. Obviously, we in PET Labs, we take these stable isotopes and we put them into a cyclotron and we change the structure of the atom. So we take away or add a proton and take away or add neutrons. And so we change the structure of the atom in a cyclotron. That's the purpose of a cyclotron. In terms of our production processes, ASP and quantum enrichment, it's not possible for us to change the structure of the atom using that.
And Chris Jordan asks, how exactly has Russia been disrupting the supply chain? Are they controlling supply or price? And how is it going to affect ASP?
Yeah, so actually, to my knowledge, no country has embargoed the export of isotopes from Russia. You touch isotopes every day in your life, and they're required for certain basic things such as energy, and so it really isn't possible to not have the supply of them. So far there hasn't really been any supply side issues or whatever. Russia has historically not been a great supplier of isotopes. Some months they're there, some months they're not there. Customers have been looking for a new supplier for decades. And I guess, the last 20 years has been about globalization. Maybe the next 20 is about deglobalization and countries wanting to have more certainty over supply chain of critical materials. And that's really helping us as a company to talk to potential customers and deliver them solutions to challenging problems.
And Joanne Scott asks, is a process by which you enhance proprietary?
Thanks. Yeah, so our process is proprietary. It's only known to our scientists and to our team. Our processes are not protected by any patents. We probably wouldn't be allowed to issue patents on our processes. By issuing a patent, we're kind of telling the world how to do exactly what the IAEA, the Non-Proliferation Council, don't want the world to know how to do. So, our processes are governed by the International Atomic Energy Agency and by the Non-Proliferation Treaty. So, when you look at our production sites where we produce isotopes, there's very, very secure locations. Only a very few people allowed to get and have access to technology. There are no phone lines or computer lines into our manufacturing facilities or our research facilities. No phone lines or internet lines out either. At the end of the day, every hard disk from the computer is put inside a safe, inside a second safe, inside a locked room, inside a metal-controlled area, or a barred-controlled area. Every car coming in and leaving is searched on the way in and on the way out. No laptops are allowed in. And actually, in terms of people who have access to the technology, not even I'm allowed into the R&D facility by myself. I have to be accompanied by one of the people who've been approved by the Non-Proliferation Council as being allowed to have access to the technology. So, yeah, it is proprietary. We're very lucky to be protected by or governed by these very strict protocols and processes that stop kind of the proliferation of this kind of technology, this knowledge, and we kind of rely on that to keep our technology proprietary.
Perfect. Mary Pena asks, who else is producing carbon-14? If you can produce the world's supply, how will you get the competition's business?
Yeah, so historically, carbon-14 has been produced solely by one nuclear reactor in Russia. And I'm told there hasn't been any production for the last couple of years. There's been no supply into the US since probably June of 2022. And so there's a real supply side problem. Most companies have always kept a year or two's inventory because of the inherent fragile supply chain. And so when it comes to taking market share and business, I'm not sure there's really any other competitor out there right now. We're not responsible for the selling of carbon-14. We actually just sell it to our Canadian counterparty, and they then turn it into the finished products, the finished salts, and they sell it into the marketplace. So we're producing carbon-14 on a tolling contract for a Canadian customer, and we actually love that type of relationship. That's perfect for us. We haven't got to deal with customers or any of the kind of the selling and the supply chain downstream. We just do the enrichment.
And Colin Clark asks, are your year-end numbers expected soon?
Yeah, I think we have to file our 10K by March 31, which I think falls on a Sunday this year. So maybe we'll get till April 1. But yeah, around the end of March is when we'll file our 10K.
Sylvia Pierce says, I read an article that isotopes are important in everything from oil and gas exploration to national security. Sylvia's been a shareholder since she saw you on the Emerging Growth Conference, happy to say. So when can we expect the company to begin cash flow?
Yeah, so first of all, thank you for your interest and your support. So in terms of generating free cash, what we've said is that both plants should start generating free cash flow and revenues, around the middle of the year. So whether that's June or July, difficult to tell, but around the middle of the year. And we started processing the carbon feedstock for our carbon-14 plant in December of last year. That's a 6-month process to produce product. So we're producing product right around kind of the end of June. Subsequent batches will take about 3 months rather than 6 months. This first batch takes a bit longer. There's certain parts of the process we can do in parallel in subsequent batches.
A few questions from Brito de Rose. Is the stock distribution for QLE 1-to-1?
So I can't tell you what the stock distribution is going to be at this moment. It's going to depend a lot upon our tax advisors, tax accountants, and bankers and what have you. Our goal is to make this as tax efficient as possible for investors, but also to spin out as much as we can with that, whilst making it tax efficient. The goal I think is in the second half of the year to try and do maybe an IPO, raise some additional capital into QLE, and at that point in time, coincident with that IPO to spin out a proportion to investors. So I guess stay tuned over the next 3 or 4 months, and we'll try and give some guidance on that as we approach the record date.
And any MOU for Silicon 28?
We haven't signed any MOUs for Silicon 28, although we are talking to a number of semiconductor companies and governments who require it. And so I think it's kind of likely we'll enter into a supply agreement in the next sort of 6 to 8 weeks or so. We'll see. Maybe a bit sooner. But yeah, we'll see.
Jennifer Scuti asks if the plant in South Africa can also manufacture other isotopes that are under development.
So we have 2 plants we have two plants almost finished or finished and one in construction. The first plant, carbon-14, is very specific to carbon-14. It enriches methane. It's a radioactive version of methane. It's difficult to put much through it at the same time. With some retrofitting and some 3 or 4 months of changes, we could do something else in that plant. But that's really specific for carbon-14. Our larger plant at Kudersport, which is about 30 times the size of our carbon-14 plant, can process multiple isotopes. And we've signed 2 contracts already from that plant, and we expect to sign some more fairly soon. And so that can do multiple isotopes. And then our laser plant, our quantum enrichment plant for ytterbium-176 can also enrich things like nickel-64, zinc-67, maybe zinc-68 as well. And so again, that can process multiple isotopes as well.
And Douglas Veen has a few questions. Let's see how many we can get in the last few minutes. First of all, how many competitors do you have?
The answer there is not many. When you look at most isotopes that are produced, Rosatom, or the Russian Nuclear Energy Agency, is basically the main competitor. Urenco, a UK, German, Netherlands kind of partnership, produces some stable isotopes, but not all of them. And that's it, really. There's not many competitors out there.
And he also asks, what do you see 2025 revenue to be? Can you project anything?
We haven't given any guidance, so I can't really comment on that, I'm afraid.
And is the company a target for takeover, or will the proprietary of the business allow you to grow at a rapid pace?
So I think we will certainly be able to grow at a rapid pace, and that's our expectation. In terms of a takeover target, when I look at possible takeover targets, there probably isn't a single company that would want to take over or acquire both sides of our business as one. That's another reason why splitting the company into 2 makes a lot of sense for shareholders, because there are lots of potential acquirers for a nuclear fuels business and potentially lots of acquirers for a nuclear medicines business. But the 2 together, it's difficult to see where the match, where synergies and who may have interest in the whole group. And obviously, our goal is to do whatever we can to enhance, to make the most shareholder value that we can possible. And so thinking about longer term opportunities, we have to think about that now.
And last question, clarify if you're building the plant in Ireland, and what does that structure look like, and how do you benefit?
Yes, we'll actually build the plant in Iceland, so that's probably my accent. So Iceland, not Ireland. So Iceland benefits from a lot of cheap energy, and we use a lot of energy. So think about in South Africa, we pay between 30 and 40 cents per kilowatt hour, whereas in Iceland, we'll pay less than 5 cents per kilowatt hour. So it'll really enhance our gross margins, but it'll also allow us to really bring down the cost of production and the price we can charge for these isotopes and become the lowest cost producer of isotopes in the world, and ensure that we'll be the dominant global player. We'll own these plants, so they benefit us by basically adding to our top line, adding to our growth.
Wonderful. All right, Paul. Well, thank you so much. We enjoy following along with all of these important updates, and I guess we could see the wheel behind you because it's turned dark.
Yeah, yes. Well, thank you for joining me in London tonight.
Yeah, it's a beautiful view you have, and great work. Thank you so much. Please come back on the conference with some updates.
Great. Thank you. Have a good day.
Okay, everyone,
Bye.
stay with us. We'll be right back.